look at molecular geometries. Again, a lot of this we had in Honors Chem, but some of it is new. And I don't think you're going to find it to be very difficult. So let's go ahead and get started. Okay, so what determines the shape of a molecule? Well, if you remember from last year, what we said was that electrons here and electrons here are going to repel each other, and electrons here and electrons here. Because they're all negative, they're going to repel other pairs, and they're going to be spaced as far apart as possible. Okay? So whether they are bonding, as in the case of the NH, or their lone pair, they are going to repel each other, and therefore space themselves as far apart as possible. And this will allow us to predict the shape. Now remember, when we think about the shape, we want to think about how many places around the central atom we have electrons. And we call those electron domains. And it doesn't matter whether it's in a bond, or whether it's a single bond, or a double bond, or a triple bond. They count as one domain. And lone pairs also count as one. So here we have 1, 2, 3, 4 domains around the central atom. Okay? So the valence shell electron pair repulsion theory, also known as VSEPR, is the theory that leads us to these shapes. So what it says is the best arrangement around the central atom is based on the maximum separation of electron pairs to minimize repulsion. So valence shell, so we're talking about valence electrons that are involved in bonding, electron pairs, and it's the electron pairs around the central atom, and it's all about them repelling. So that's what VSEPR is. Okay. So these are 6 different geometries, all of which you're going to need to know. Actually, there's 5 different geometries for electrons, where there's 2 domains through 6 domains around the central atom. Okay? And in all cases, what you'll see is if there's just 2 domains, they're going to be equally spaced apart at 180. If there are 3 domains, they're going to be equally spaced apart at 120 degrees. In a 3-dimensional space, for 4 domains, they'll be equally spaced apart, and so on and so on. Okay. So all we need to do is count the number of electron domains, and in this case we have 1, 2, 3, 4. Those electron pairs are going to be equally spaced apart, so the electron geometry here is tetrahedral. Even though there's no atom up here, there are lone pairs which also take space just like they do here. Okay, so the electron geometry is tetrahedral. The actual shape is not tetrahedral. Okay. So molecular geometries then depends on VSEPR, you know, where the electrons cause this, are located so that it causes this separation of pairs. And then the molecular geometry depends on where the atoms are. So even though I have a lone pair here, there's no atom sitting up here, so this ends up becoming trigonal pyramidal. So I still have these same separations of these 4 pairs, 1, 2, 3, 4, but because there's no atom up here, I do not have a tetrahedral molecular shape. So molecular geometry is defined by only the atoms in the molecule, not the non-bonding pairs. So within each electron domain, there might be more than one electron geometry. So if I have 4 domains around the central atom, it's possible I have 3 different, they're all electron geometries are the same, but the actual shape of the molecule is going to be different based on whether or not these are lone pairs or bonded pairs. So if I have a bond with an atom on each of the electron domains, I have a tetrahedral shape, equally spaced apart. If I have one lone pair and only 3 atoms attached, I'm going to have trigonal pyramidal. You know, this nitrogen is going to be sticking up. And if I have 4 domains around the central atom, but 2 of those are lone pairs and not bonded pairs, and I will have a bend shape like I do in water.